Welcome back, everybody. So let us get back to the material. So I was in the middle of explaining to you the difference between an information need and a query, and the fact that there might be an ambiguity, that the query to the result is fully deterministic. So this is always 100% successful. It's a mathematical truth. However, this is where there is a bit of margin of appreciation because the information need isn't an actual query. Know that, so there are other ways, right? In that case, we are using Boolean queries. In the case of ChatGPT of large language or large language models, you would have word embeddings, but the problem is still the same. You always have some sort of mismatch between the representation of the information and the information need. And the best proof of this is the hallucinations that even large language models can have. So it's not 100%. All right. In fact, if you come back to a few centuries ago, Leibniz was even asking the question, can we have such a thing as a fully unambiguous human language? And the answer is no, you can't. That's just not possible. All right. So how do we assess this? Well, we need to look at what we have. We have a system that we'll implement that takes a query and returns results. So you have a human with information needs in their brain and results that pop out of the system that may or may not be relevant to the user. So it means that you have two dimensions. You can return or not return a document. That's what the computer does. And a document may or may not be relevant to the human being, right? So that's two dimensions of two possibilities. So you have how many cases? 4. 3, yes, if you don't assess the relevance of the documents that are not returned. 4, if you would also do that. So let's look first at the documents that are actually returned. And I'm going to classify them as relevant or non-relevant. So in the light green, you have the ones that are relevant. In the dark red, you have those that are not relevant. And we have a name for this. So we call all of these return results the positives, or I just put return results to be more precise, but we could also say positives. The true positives are the positives that are relevant to the user. So then you got it right, the system got it right. And then you have the false positives. The false positives are documents that are returned by the system, but they are not relevant to the user. So you returned too much to the user, right? And of course, in a good system, you have a lot of true positives and you don't have a lot of false positives, right? So ideally, you would like only true positives. But then this gives us an idea for a first measure or metric of measuring the efficiency of our system, because we can just take the ratio of true positives compared to all the returned documents. Yes. And we call this the precision. So the precision, you need to know that by heart, it's the number of true positives divided by the total number of positives, the returned documents. What's the precision right here in that case? Half, yes, 50%, exactly. So in that case, it's 8 divided by 16. So that is 50%. Who agrees? Okay, so this is kind of okay, man. What is the precision here? Everybody at the same time, precision is? Everybody? 100%. Yeah, exactly. And the other precision is? 0, exactly. Perfect. And here? 40 other possibilities. So let's do the division. True positives, how many of them? 8. Total number of positives? 10, so 8 divided by 10 gives me 80%, right? Okay, wonderful. So we have the relevance and non-relevant documents. So let me add the other dimension. So now we also have the results that are not returned. And now we have this annoying, well, on Zoom, you don't see it, but, or maybe you do see it on your screen, but in the lecture hall, you have this annoying toolbar. But somebody once gave me a trick that you need to open this and close it, and then it's gone. And by the way, I'll answer to some Zoom remarks just after that. So what do we have here now that we have the non-returned results? Well, we have the false negatives and the true negatives. So the negatives, this is everything that is not returned by the system. They can be either true negatives. It means that the system got it right. It did not give you documents, but these are documents you're not interested in, so it got it right. But the false negatives, they are a problem because you were interested, you would have been, it's a subjunctive conditional, you would have been interested in these documents, but they were not returned to you. So these are false negatives. So if you look at this whole two-dimensional classification of all the documents, so you have the entire collection here classified in 4 categories. We like this, we like this, we don't like this, we don't like this. Okay? So this is, ideally, we would only have documents in the diagonal right here. So let's use another metric because the first metric was only looking at the returned documents. Let's now, instead of looking at the upper row, let's look at the left column. So we have all the documents that are relevant to the user. Note that I'm leaving aside the discussion of how do we know that they are relevant to the user since the user didn't see them, right? So there are tricks, there are studies, there are ways that you can actually build this. So we are kind of assuming that we know, but it's not trivial to know that. But let's assume we know what is relevant to the user. So now the recall is going to be the true positives divided by everything that is relevant to the user. I didn't get the light dark correctly on that one. So it's the true positives divided by the relevance. So what is the recall? It's called recall. What is the recall in here? I'm hearing 50. Who thinks 52? No, who thinks 50, 2 TOO? Okay, yes, awesome. So this is indeed 50%, 8 divided by 16. What is the, well, it's the same as the other time. So here the recall is 100%, and here the recall is 0%. So this is awesome. This is not awesome. Well, sometimes it is, but I'll come back to that. Now the recall here is 67%. That would be 8 divided by 12. It's the 2/3 of it. So we have the precision, we have the recall. Who already saw that in the machine learning lecture? Right? Because indeed, it is also used in machine learning. This is the same thing. This works exactly in the same way as in machine learning in the classification systems. In fact, there is another way of calling these false positive, false negatives, which is type 1 errors and type 2 errors. The problem is that I never managed to remember what is the type 1 and what is the type 2. So I'm not taking the risk and I just say false positives and false negatives. But they are called in practice type 1 error and type 2 errors, right? And depending on the context, you might be more accepting of type 1 than type 2 or more accepting for type 2 than type 1. It really depends because this is real life. There are real people sometimes who might see the consequences of these errors. Okay, so we have these two kinds of errors and we have two metrics. We have the precision and we have the recall. To quantify, in the case of precision, we quantify type 1 error. And in the case of the recall, we quantify type 2 error. And now I realize that I just got an Eselsbrücke to remember type 1 and type 2 because I first talk about precision and then recall. And precision is the first one, type 1, recall is type 2. Okay, now I will be able to say type 1 and type 2 correctly. Okay. What's the precision here? 80%, right? And the recall is 50%. Okay, so whatever, so this can be exam questions, right? Imagine I give you this or I give you a matrix with counts and I ask you what's the precision, what's the recall, and so on. So who is able now to answer precision and recall if I give you something like this? Who can do it? Okay. Everybody, awesome. So this is, in that case, high precision because we have 80% of precision, but the recall is not so good. Here we have high recall. In fact, the recall in that case is 88.888%, and the precision is 50%. Yes, so here we have high recall. Now, can we have systems that have both high recall and high precision? It's very tough. Getting both of them at the same time is very tough, and you typically just put some balance in between the two and try to find a compromise, like what do you care the most about? Do you want to be in the middle? Or, you know, it's basically a design decision for what you want to achieve. All right, but I'm stopping here because in fact, we are going to have a full week spent on the evaluation of systems, and you'll see that besides precision and recall, we also have other metrics like specificity and so on and so on. So there's actually plenty more things that we can do about this, but false positive, false negative, precision, recall, and the compromise between the two, this is the basic of the evaluation of some systems. And now you understand that this is about the information need and not about the query. Because if I didn't consider the information need and only the query, you need to understand that then I would only have true positive and true negatives and never anything as type 1 or type 2 errors. That would never happen because, again, it's a mathematical truth. It's only when you look at what we have in our brains, like the information need, that we start seeing these false positives and false negatives. Okay. Now, I promise to you something better than incidence matrices. But first, I need to tell you why we need something better, because you might have thought, you know, after all, incidence matrices are perfect, right? They do the job. They can tell us the documents that we need. So what's the problem with incidence matrices? Well, the problem has to do with the size. Because we are going to be using some parameters in our system when we talk about an information retrieval system on a very, very high level of abstraction. And there are two letters also used by the book. It's uppercase N, uppercase M. So big N, big M. And what we call big N and big M is this. Big N is this. It's the number of documents, N, and M is the number of terms right here. And the typical number for, I would say, let's call it a 0815 information retrieval system, would have 1 million documents and 500,000 terms. So 1 million documents and 500,000 terms. 0815 means in English 8:15, and it's just a way in German of saying that something is just standard. All right, so 1,500,000. Now, do you see the problem now? Because if you look at the number of Booleans that we have to put in there, now we start having a problem. Because it's 500 billion bits, so 500 gigabytes. Yeah, it fits on the hard drives, right? You can put that on the hard drive on your machine, but what do you have left after that? Not much. So that actually takes a lot of space, not to mention the traversal every time of 1 million of documents. Even though you could argue nowadays a for loop with 1 million values, that's actually nothing, right? But still, there is a scalability problem here. So how many zeros do you think we have in there? And here you need another real life fun fact, is that typically a document will contain in this 0815 system, it will contain 1,000 terms. So in every document column, you have 1,000 ones, and then the rest is zeros. But if you realize that it means 1 in 500 is going to be a 1, right? So that is something like, I'm not very good at math, but this sounds like 0.2% of ones. And 99.8% of the matrix is just filled with zeros, right? So this is, yeah, I got it right. 99.8% of the matrix is basically empty, 0. So this is a huge waste of space. And when a computer scientist sees something like that, they just have this irresistible urge to optimize and find something better. And that better thing is what we will call the inverted index. We understand that this is not appropriate, the incidence matrix, right? It's great for mathematicians. As a mathematician, I love it, but for an implementation, that's just not good enough. Okay. So this is space inefficient. Now, let me open a parenthesis, because I said, you told me over Zoom, where are you here? Somebody talked about grep, right? I don't know grep. You don't need to worry about that. because grep was just, it's a tool basically that allows you to search words in text documents, but we will not use it, right? So the only reason why I talked about grep was as a hypothetical tool we could have used, but we don't. So you don't have to worry if you don't know grep. Were there other pending remarks in the Zoom chat? Nothing? All right. Okay. All right, so everybody agrees the incidence matrix, great for mathematicians, not great for computer scientists or for an actual working system. Okay, so if you're a startup using that, you're going to burn a lot of investment money in order to build that thing. So what do we do about it? And I have a question. How do we solve the 99.8% sparsity issue? Give me a few seconds. I think that's the one right here. Yes. So how do we solve that? First, so you just created your startup and you're lucky enough to have a lot of investors pouring money because that's an AI startup. So you rent a cluster of machines on Amazon and you hope that the ETH finance and controlling department doesn't complain. Or we list only the terms used by each document rather than mark all terms with zeros and ones. Or we list only the documents containing each term rather than mark all documents with zeros and ones, and an S too much. Or only Google knows that you have an ADA and you can't tell us. Wow, some of you are ambitious. So you would rent a cluster of machines. Then we have half-half between, do you want to list the terms for each document or do you want to list the documents for each term? That is an interesting question, right? So who do you think is right? Is the majority right? Or is not the majority right? You can still change your mind. Nobody seems to be changing their minds. Some people do change their minds. Just, something's happening. Oh, okay. Well, let me stop making you wait. The majority was correct in that case. It's not always the case, but here the majority was correct. Indeed. Why? Because if you build a structure that for every document gives you the terms that are in it, that's actually your original collection. So you did not gain anything from that because you're just repeating what you already have. But if you, on the other hand, you list the documents per term, you basically invert the whole thing. That is an inverted index. And now you can use that to query. And I will show you why. You will see on the concrete examples. So you do need that shift between grouped by document, which is the original collection, right? Hopefully, if you go to a library, the data is organized with all the words within each book, right? You don't go to a library and see the words on the shelves with the documents inside. So this is why we invert things for the lookup. Okay, so this is why the majority is correct. All right. Yeah, let me get back. 6, I think. Okay. So this is the problem we have. We have 0.2% of the matrix that has ones and everything else has zeros. Of course, here it's a simplified example on the slide, so it's actually not that sparse, but just to illustrate. So the idea is that we look at every term on every row and we list here the document. So instead of having zeros and ones as many as documents, I ignore the zeros now and I list the IDs of the document. So for T, I will explicitly list 1, 4, 9, 10, and so on. It's equivalent, right? It's just another representation. And in fact, more exactly, this is what we'll use. So if you look at this, you should convince yourself that this is equivalent, right? It's just another way of representing the same thing. I still have one term for every row. So this is why I put the terms on the rows in order to not disturb you too much when I do that swap. But now instead of the zeros and ones, I have a list of documents IDs, okay? This is called an inverted index or an inverted file by some other people, right? But an inverted index. Okay, so now a bit of terminology. This is called a term, right? That I already told you. So in fact, the word term is used whenever you have it in the index. This is when we use the word term. And I know when I speak, it's very annoying. I don't know how to get that, but I keep saying the word term, the term. I don't know how to basically, because there's this double usage of term and word when I actually speak and explain things. And then there's term and word that is actually the terminology of information retrieval. Anyway, we say term when it's like this in the inverted index. This is called a dictionary. The dictionary contains all terms. In fact, the dictionary is not just that it contains all terms, it also has some data structure that we'll look at later. So the dictionary is some data structure that organizes the terms in the inverted index. Dictionary. Vocabulary is used as the set of terms, then you call it vocabulary. And when you say dictionary, then you also have that additional structure that I'm not showing here, but we'll take a look at it next week probably. Then we have the documents. Here they are. So we have one document, that's document 4, but you see that it appears multiple times, right? Probably 1,000 times if it has 1,000 terms. So this is the document ID. But now there is a subtlety, because how do I differentiate between document 4, so which is a book I can hold in my hands, and this very specific 4 right here? How do you make the difference? This is not quite the same thing. So this specific 4 right here is called a posting. A posting is a pair with a term in the document. This here is the posting X4. But I don't write X here. Why? Because it's there. So since anyway, all of my postings here, they are for term X, then I don't repeat X, I just write it once here. But this is in fact X1, X3, X4, X7, and so on. So this is a posting. So again, a document corresponds to one number that could appear multiple times, and one very specific number here is called the posting. That is a pair with a term right here and a document. For whom is that clear? All right, so we have the terms, the documents, and the postings that are pairs with one term and one document. Okay, and I'll keep repeating again this terminology: term, posting, type, token, and so on. I will clarify, it has very, very precise meanings. Okay. More exactly, we call that a non-positional posting, because there are also positional postings that we will see later. And that refers to what one of you said earlier. We forgot the position in the document. So this is why this is a non-positional posting. It only tells us X appears at least once in document 4. So it's a non-positional posting. We don't know where in document 4. Okay. So term, document, posting. It's blocked again. Hello? Ah, yeah. Okay. And here we have, it wasn't reacting, we have the postings list. Well, a postings list is just a list of postings, but it's typically all of the postings that are associated with one term. And a postings list, in fact, you can see as a sorted list of integer. It's always ascending, always sorted by document ID. So this is called a postings list, okay? Again, since these are all pairs term documents, but they all have X as the first item in the pair, so we don't repeat X everywhere. Okay, and collectively, all of that together are called postings with an S at the end. So one posting here, and the postings, all of them are all of these. Okay, for whom is that clear? Term, document, posting, non-positional posting, vocabulary, dictionary. All right, so this has a very precise meaning. And this is the index. The whole thing is an inverted index. In fact, we will even call it the standard inverted index. Why? Because we're going to modify it and add a few bells and whistles later, but this is the standard inverted index. Oh, maybe the standard one also has this. I will add just one thing to the standard one. I will add here, before the postings list, what is called the document frequency. It's just a count, right? It's only a count of the number of postings that follow. So you see here, how many you have? 1, 2, 3, 4, so you put a 4. 1, 2, 3, so you put a 3. 1, 2, 3, 4, 5, you put a 5. 1, 1, 2, 3, 4, 1, 2, 3. These are called document frequencies. We'll come back to that because that will be useful for ranked retrieval. But it's common. So typically, when you have the index, you do not only put the postings list after each term, you also put, for convenience, the document frequencies in purple, right? So it's a slightly different color. All right. Let's do it. Let's build an inverted index. So I'm going to take, because it wouldn't fit on my slides if I take the entire Shakespeare corpus. So let me take just these 4 documents right here. And I'm going to build the standard inverted index. So the first thing you do is called tokenization. So I'm oversimplifying here, in fact, because technically, it's more complicated than that, but for the purpose of today, I just look at the spaces and separate every time there's a space, I just cut it there, right? So if you tokenize by space, this is what you end up with. There is something else that I'm going to oversimplify for today, which is that I'm just removing the uppercase, lowercase, and so on, and I'm going to assume that this is enough, right? So for example, I'm removing all of that and simplifying. Reality is much more complicated than this. So again, today I'm oversimplifying because I want to focus on building the index structure rather than post-processing the words of the documents. So you see, now that I've done that, you see all of these rectangles right here, here, all of these rectangles. These are called tokens. Every one of these is called a token. We tokenize the documents, and now we have tokens, right? Now I'm just reorganizing them. Imagine they're on a table, and I'm just grouping them nicely by color. So no, sorry, not by color. I'm grouping them by text that they read the same. So for example, is there an example here? Oh, sorry, not yet. I was too fast. I wrote too fast. All I did here is who knows what the transpose of a matrix is? Okay, I just took the transpose. So all I did was, I don't know, mirror the table in some way, and now my rows are my columns. But this is really the same thing. It's still grouped by documents. Now, what I do is that I sort them alphabetically, like this. So now you see the colors are all mixed because now it's alphabetically sorted by word. And now you see that there's multiple occurrences because now you see hour in yellow and hour in red. So they are in document 1 and in document 2, right? What I did here too is that I also added this, the number of the documents, right? I did not only take the transpose, I also added document 111 for this, document 2, document 3, document 4, and now I have my pairs, right? One term with one document. So now I have my pairs, and I resort the pairs sorted alphabetically by term. Who is following? Okay, very good. So now I'm going to merge. So you see I have 3 times the same term here with 3 different documents on the right. So I'm just going to write the term just once. And now I'm just putting the document IDs right there together. We know that the term com appears in document 1, 3, and 4. The same goes for hours in 1, 2, 3. What else do I have? It appeared twice, but we forget about the number of occurrences because we don't care. It's the set, and so on and so on. So we have now that merge, still sorted alphabetically, but now it's sorted alphabetically, and the terms are now unique because I merged And then I just slightly make it nicer. It's the same thing, but a bit more with a bit of extra cosmetics. And now I have something that resembles a standard inverted index. In fact, this is my standard inverted index. I only need to add the counts, as I did before, which most of the time is just 1, but for com and for hour, there are 3 postings, so I put a 3 instead. This here is my standard inverted index for the original documents. Who agrees? Who would be able to build that for any set of documents? Okay, assuming the oversimplification, right? I'm not getting into how you tokenize and so on. Okay, now, if we query with that standard inverted index, how does that work? Like to find hour, well, we know it's alphabetically sorted, right? So it's you do it like you learn in primary school how to look up a word in a dictionary with a binary search, right? But technically, as a human being, we are pretty efficient to look a word in an alphabetically sorted list. So we find hour. By the way, what's the complexity of looking up a word in an alphabetically sorted list? O of n, O of 1, of log n, exactly, that's logarithmic. We'll dive a bit more into these structures. You probably guess the kind of structure we're going to have. Anyway, in O of log n, I can locate that term right here. And now I know that I return the documents 1, 2, and 3. So these are my results. And now, typically, when you implement a search engine, you might even show the snippets with the word highlighted in some way in bold or something, and so on. Okay. Now, what about an AND query? So what you need to do is then, so I have hour and com, so I take the 2 right here. Of course, I pick them because they are interesting, because the other ones are just singletons, right? So I just try to pick an actual example that is more complex. We need to compute the intersection, right? Com and hour, we need the documents that have both of them. So it needs to be the intersection of the postings list, okay? Who knows how to compute the intersection of 2 sorted lists? What's the complexity? O of log n, quadratic, exponential? Yes?
O of n, if n is the length of the longer list.
Yes, exactly. It's linear, basically, O of n, absolutely. So the intersection can be done in O of n, where it's the length of the posting list. If you consider the length might be different and you call them n and m, then it's log of n plus m if you want, in the same order of magnitude. But this is exactly the idea. All right. So now we have the intersection, and you agree that there's only 1 and 3 in there, right? So we have now document 1 and document 3, and you can see they contain both of our terms. So we are basically doing the job, right? This works. What about OR? What do we need to compute then with an OR? Not the intersection, but the, everybody at the same time, the union, exactly, the union, right? So now the union of this is 1, 2, 3, 4. And we have then all documents are actually returned. They have either the term hour or the term this. I think it was hour or this. Yeah. Okay. But let's come back to this algorithm that indeed is linear about the intersection of 2 sorted lists. We actually did it as a PowerPoint karaoke a few years ago, this one. Does anybody want to do the PowerPoint karaoke with this? Once, if I just click, 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 and you explain what's going on? Any volunteer? Otherwise, I'll do it, don't worry. We have no volunteers? Okay. Do you still have these PowerPoint karaokes with FIS? A few years ago, I think it was quite funny, actually. You were given slides that you know nothing about, and you're just supposed to speak in front of them. All right. So let me do it. It's just, it's unfair because I know what's actually on the slides before I tell you. So we initialized with 2 pointers. So this is 2 lists, list A and list B. They correspond to 2 terms that I picked, and the posting lists that correspond to them. It was because it was some AND Boolean query, right? I want the 2 terms. So now, what first thing I do, I initialize my 2 pointers on the left, the head of the list. You can consider them singly linked lists. Is 1 equal to 1? Yes, 1 is equal to 1, right? So I output the 1. And then I move both pointers by 1. Now we compare again. Is 2 equal to 3? No, it's not. So what I do is that I look at the lowest number, that is 2, and I move just the lower number by 1, like this. Now, is 3 equal to 4? No, it's not. Now the lower number is 3, so I move it by 1. Is 4 equal to 4? Yes. So now that's a match, and I put it in the output. Now I move both pointers by 1. Now 5 is not equal to 6. So I move the pointer with the lower number by 1, that would be 5. Is 6 equal to 8? No, so I move the lower number by 1, that would be 6. Is 7 equal to 8? No, so I move the pointer with the lower number, that is 7 by 1. Is 8 equal to 8? Yes. So I write it in the results at the end and move both pointers by 1. Is 9 equal to 11? No, so I move the pointer to the lower number by 1. That would be 9. Is 10 equal to 11? No, so I move the pointer with the lower number, that would be 10, by 1. Is 11 equal to 12? No, so I move the pointer to a lower number, that would be 11, by 1. Is 12 equals to 12? Yes, and I'm done. Who understood? Who can implement it? Okay, wonderful. So this is how you intersect two lists, and you can see that it's linear, basically in the length of the list, or the sum of the length of the lists. All right, it's pretty good, right? We can look up the terms in logarithmic time, and we can traverse the list and intersect them in linear time. What about the union? If I have an OR, who would be able now to do the union? It's quite similar, right? Any volunteer for the PowerPoint karaoke? No volunteer? Okay, let me do it. I'll be quicker though, because you probably understand how this works. So 1 is equal to 1, so I put it just once and move by 1. Now I take the lower one, that is 2, I output it and I move by 1. Now the lower one is 3, I move by 1. Now the lower one, when it's twice the same, 4, so I output it and move the 2 by 1. The lower one is 5, I output it. Now the lower one is 6, I output it. The lower one is 7, the lower all 8 on both sides. So you see, I was just running out of space. I think it was because the slides back then were 4 times 3, and now it's the 16:9 format, but I could actually have used some more room on the right. Anyway, that's the only reason why it's going like this. So I moved the 2 of them. The lower one is 9, the lower one is 10. Now it's 11. And 12. So you see, it's very similar to the intersection. The only difference is that when there's a mismatch, I still output the lower one in the results. Other than that, it's the same. And that's also linear, right? Okay. Who would be able to implement a not, maybe indirectly as an AND not or not? You can basically use exactly the same algorithm, but you just invert your actions, right? You output if it's not there, you do not output if it's there. That's basically the idea. Maybe you can try it in the exercise if you want to support the not as well. All right, let's now talk about optimization. Because a query might not just have 2 terms, right? If it's just 2 terms with an AND or a not, we just do the intersection or union. But maybe the query is going to be very complex with a lot of ANDs, a lot of OR. How do we deal with this? Is there any strategy to keep it efficient? The answer is yes. So let's start with multiple ANDs. I have multiple terms with ANDs. Now, how do I optimize this? Well, you probably want to start with the posting lists that are the smaller ones, because then you're going to work with small structures from the very beginning and use less space. How do you know which terms have the shortest posting lists? Do you need to traverse the list? No, you don't, because you have the count on the left. This is why we put it there, in fact. So we do have the count directly sitting on the right of the term. So we know, for example, ETH might have 10,000 documents, Zurich might have 100,000, and Bibliopol might have 10 documents. So we just take the smallest ones. So in that case, Bibliopol and ETH. So I rearrange that in an increasing order. And now I merge Bibliopol and ETH. I know it's going to be less than 10, maybe 10 or less than 10, but not more than 10, because that's the intersection. And then when I do AND Zurich, it's still going to be less than 10, right? So do you agree this is the most efficient? Who agrees, right? If I sort it the other way around, I'm going to have huge posting lists. I'm going to have a list with thousands of IDs if I do it with ETH and Zurich first, right? So I do it by increasing document frequency. And the idea is that you try to maintain this in memory. So your your output and you can slightly modify the algorithm. You know that you can do it in place or create a new structure and so on. So we can slightly adapt that in such a way that the intermediate result is just kept in memory, and you just then reduce the size of the list by suppressing contents as you make progress. Okay. What about the more complex case? Well, there is a trick. Who remembers, I hope I'm going to get that terminology right, who remembers well, if I see your hands not raising, it means I got it wrong. The normal conjunctive form? Yes, hands raised, I got it right. The normal conjunctive form. If I give you any Boolean formula with and, or, not, and so on, you can factor it in such a way that it's a bunch of ors and a bunch of ors and a bunch of ors and so on and so on. That's called the normal conjunctive form, and there is also the normal disjunctive form. I hope I didn't swap them. But basically what I'm saying is that you can always rearrange in order to have and inside every factor, you have the or. You might have a few nots, right? The individual term might have a not or not a not. But basically, you can always rewrite your Boolean query as a list of ends. And within each factor, then you have a list of terms separated by or. So the end, you just take the minimum counts. You can approximate the size, so you sort them. For the or, you can, if you want to approximate the sizes to sort them, you can approximate the size of an or with the sum of the counts. So if you're doing an or between a term with 5 documents and another one with 100, then you can approximate with 105. And then once you approximate each factor, then you can sort the factor by increasing estimate. For whom is that clear? All right. Okay, and for the not, you can adapt all the algorithm by just virtually walking down the negated list. So you just invert your actions, as I said, right? What you would have done, you don't do, and what you would not have done, you do. Okay. So for the purpose of the exercise, the TA team is very generous. They took care of the grammar and so on. So you do have the grammar. It looks like this. Who heard of context-free grammars? EBNF and so on. Okay, so we are giving that to you for free. You don't have to take care of that. You will have a parser and so on. So the query comes directly parsed as an abstract syntax tree based on that. And then you can go ahead and implement this, all of this in Python next week, right? This week is I think, just testing the Python notebook, right? So Python tutorial. And next week, you will have to implement your first system where we give you the parsed query for free. Please, 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 please read the chapters of the book. You have copies in the libraries right here, right there. It's also online, I think in nlp.stanford.edu, you will find it there. Please read the chapter. It's the same thing or very similar to what I'm telling you, but it gives you another angle, another way of explaining things. So you should really be reading that book. Any questions? Yes? It's just, you can basically have a lower and an upper bound, right? So if you have an or, the upper bound would be the sum. And basically, we want the worst case, so we take that as an approximation, right? That's the idea. But of course, it's a very coarse approximation, right? Maybe you can also improve and find something better, right? Okay, who is hungry? Okay, so go grab some food. Enjoy the rest of the week. I'll see you next week at 10 a.m. Go to the exercise. There's the exercise classes this afternoon at 4. And after that, have a great weekend. Thank you very much.